Okay, looking at page 583 of the text and page 10 of the notes I gave you, that's where we're starting. Remember from yesterday, if we uh, uh, if we increase the temperature of a reaction, we see that the rate constant, remember, it increases exponentially. That's because as you increase temperature, you are increasing kinetic energy. And since kinetic energy is related to the velocity, and you see that the velocity, you know, kinetic energy is related to the square of velocity. So the more kinetic energy we lost, the more velocity these molecules have. They're moving faster. What does that mean? That means that they have more collisions with each other. More collisions, more reaction. More reactants changing to the products, because if we take a real simple model, like I'm messing up this nice meat. I'll put back lab assistants.
That's my job.
Yeah, they do work. They earn their keep.
It was inevitable that the job was going to be a matchup again.
That's true. That's true. Okay, now H2 plus O2 yields H2 up, right? We know it's a 2 to 2, or a 2 to 1 to 2 mole ratio. So I am, for you folks looking at the video, I'm building a model of these molecules. Don't stare at it, Sarah. I don't know. I'm going to sit on your look.
It's just when it records, it does that.
Oh, now it's gone. Okay, there we go. Okay. All right, so we have two H2s, right? H2, covalently bonded. Two valence electron from each atom pairs up, spends time around both atoms. Voila, we have a molecule, right? Lower potential. This has lower potential energy than the individual atoms. That's why bonds form. To lower potential energy, that is thermodynamically favorable. So we have two hydrogen molecules and one oxygen molecule. Okay, so they somehow need to make water, right? Okay, so what do they have to do? They have to collide. Remember, there some reactions, we don't have to add anything to it. We just put the stuff together, it reacts. It's the velocity, the kinetic energy that the reactants have already is enough to supply the activation energy. We have collisions. The more collisions we have, the more reaction we have. The more reaction we have, that changes our rate constant. The rate constant is related to temperature, to the particles, the reactants. Okay? So y'all good with that? Okay. Collision model. This is the next page, 584. Okay, so we're looking at an energy diagram here. And water, the formation of water is very exothermic. That means that the water molecules have less potential energy than H2 and O2. So our energy curve might look something like that. Now here's what all this means. This is
Before reaction.
yeah, H. this is H2, or let me draw. You got your HH, right? And okay, these are your reactants. This is your product. Right. Okay, product has less energy. Than reactants. This is called delta E, change in internal energy from thermo, right? Since the products, energy of the products is less than the energy of the reactants, that means what? Endo or exo? Exo, that's exothermic. What would endo be?
If the reactant has less energy than the product.
Right. If the reactants had less energy than the products, then the reaction would be endothermic. In all reactions, two things have to happen. Well, I'll get to rate in just a second, but in all reactions, reactant bonds first break, and that would be an increase. Energy has to be taken in. And then product bonds form. And that releases energy. So this represents the net result. You know, once you combine and get the overall result, you have either endo or exo. Now this part right here, as we mentioned, is activation energy, E subscript A. Activation energy, you know, the energy required to break the reactant bonds and get an activated complex, which is a transition state. Let me demonstrate. This is a very simple demonstration, but you've got these reactants. They have relatively low potential energy compared to isolated atoms. Okay, so before H2O molecules can form, these bonds have to break. Collisions, and we'll get to that in just a second, but collisions are how these break. You know, they have to collide, but when they collide with each other, they are transferring energy to each other, and that energy breaks the bond. They collide, energy breaks the bond.
The blonde side of the
Yeah. Okay, this is a very simplified, this stuff right here is called the activated complex. And it's not always isolated atoms. And we'll look at the graph in the book to see that. It's not always individual atoms. It could be molecule fragments. But I'm just making a very simple model here. This stuff is called activated complex. Or transition state. It means the same thing. All right, I'm going to erase this stuff. reactants must achieve transition state before products can form. We got to have this before any products can start to form. Y'all good with it? I mean, intuitively, does that make sense? Okay, good. All right. So once this is achieved, then when the atoms, remember, they have kinetic energy. They're constantly moving, right? And that's when bond formation, when these come near each other, we learned last year, there's a distance where energy is at its lowest, and that's where valence electrons pair up and make the covalent bond, right? So bonds form. And that energy is to here. Okay, so, okay, so everybody good with that? Okay. Now, before we start looking at activation energy quantitatively, I want to go through the collision model. The collision model is a theory. Remember, scientific theories explain or attempt to explain how and why something happens. Laws don't. Scientific laws just tell you something is what it is, like law of conservation of mass, right? Laws of thermodynamics. Second law of thermodynamics, what is it? Okay, what's the first law? What's first law?
The second law is disorder.
Disorder, yeah. Okay. Second law of thermodynamics, entropy of the universe is
Always increasing.
increasing. Well, why? It doesn't say. How?
More than the
But my point is, the law itself, it doesn't tell you how it happens or why it happens. It just says it happens, right? But a theory does explain how and why. Okay, that's what we're about to look at. Why does this happen? And how does it happen? Okay. For a reaction to occur, two things have to be satisfied. Number one, reactant particles must have sufficient activation energy. And here's what I mean by that. I wish that, okay, I wish I had a camera. Yeah. 584, bottom of 584 is what we're looking at, figure 12.12. Okay, remember I said these reactant molecules, they have kinetic energy, therefore they have velocities. Now, these are at the same temperature, H2 and O2, okay? Look at your molar masses. Do they have the same velocities? No. So everybody understand that? Because kinetic energy is 1/2 mass times velocity squared. Oxygen is more massive, so it would have what type of velocity compared to H2? Velocity? Lower. O2 molecules are heavier, so they're going to be slower, right? H2 are lighter, so they're going to be moving faster. So we end up with this. In a reaction mixture, we don't have all particles with the same velocities. It's a range of velocities, okay? So when they collide, and I know this is hard to understand, because it is for me, kinda not, but even your H2 molecules, they don't all have the same velocity. It's a distribution of velocities. So just bottom line, your reactants do not have the same velocities. They have different. So you have a range of activation energies that they could possibly achieve. Because remember, activation energy, particles collide, they transfer energy to each other. Okay? Since they do not all have the same velocities, that means some of them will not have, if they don't have enough velocity, they're not going to have enough activation energy for anything to happen. Some of them, if they don't have the sufficient velocity and activation energy, they collide, they bounce off, unchanged. No reaction. The ones that are faster, have more energy, they collide, activated complex. Okay? They have sufficient activation energy. Remember, once again, the reactant molecules, they've got to get to here before anything will happen. Okay? They've got to get to the hump. They've got to get right here. If they don't get here, they won't get to the product. Some don't. Y'all good with it? Number 2. Data has shown that even particles with sufficient activation energy, that got enough energy to form, where they should make that activation complex, some of them don't. Still. Why is that? That is the second criterion. Reactants must have effective collisions. That means that the molecules must have an orientation, how they're arranged in space. Orientation that favors activated complex. Martin. With my simplified model, I can't really do that. There's a picture in the book that's really good, a drawing. So I'm going to flip back to the book, page 585 at the top of the page. Looking at the top of 585, study figure 13 carefully. Really good drawing of effective and ineffective collisions. Okay, if we have this reaction, and our reactant molecules are NOBR, and if you look, let me introduce the reaction. The reaction is first described on page 584. So y'all back up to 584 for just a second. Okay, this is a reaction, and it tells in the caption of figure 11 that this is, oh, I read it wrong, BRNO reacting to form NO and BR2. So, we need a bromine molecule to form in the product, BR2. That means those bromine atoms, they need to be isolated. They need to be broken away from the reactant molecule. Let me repeat that. Since BR2 needs to form, in this reaction as a product. The bromine atoms need to be isolated in the activated complex so they are free to move near each other and form a covalent bond to make Br2, okay? You see that here in this graph, right there, that bond, you know, the the bromine nitrogen bond needs to break. If it breaks, then the bromine atoms are free to form Br2. So that's the activation complex needed to form the product. Oh, okay, thank you. Okay, so going back, and on the right-hand side of figure 11, they just show it in models. Okay, so I don't know what colors those are. Thank you, Alexis. Bromine's red, oxygen's orange, nitrogen's blue. Okay, so they're showing here that this molecule, ONBr, all covalently bonded, when it reaches that activated complex, that transition state, the oxygen-nitrogen bond stays intact. But you see the dotted line? The nitrogen-bromine bond needs to break. And then bromine will bond to bromine as the product. And the oxygen-nitrogen, that just becomes its own molecule. Do you see that the ON is the same here at the activated complex as it is as the product? Nothing else happens to them. But the bromine is what's changing, right? Do y'all see that? Okay, so which collisions will favor this? Going back to 585, let's look at these collisions. On figure 13, I don't know if I can make it. Bless you. I don't know if I can. I'll try to make it. I can't make it really well with these lines. Right? NOBR. Okay, so on the top one, we have this, right? And it's demonstrating that when they collide in this orientation, the bromines, you know, they come near each other. So this is saying that, yeah, this, let me pour hands. This can happen, and that will cause the bromine to bond together. So this would be an effective collision. Okay, and the next one, B, what they're trying to say here is if they come at each other with this orientation, the bromines are near each other, so when they collide and that bond breaks, the bromines are close enough that this attraction can occur and the Br2 bond forms. Okay, so they're saying A, effective collision, B, effective collision. On C, they're saying that the molecules are oriented this way, where bromines are far away from each other. They're too far away from each other for the attraction to occur. Attraction has to happen for a bond to form. If they're oriented where the bromines are on the outside, they collide, they just bounce off each other. No attraction occurs. So C, no reaction happens. This is not an effective collision. Okay. So, if you take a look at page 10 of your notes, let's run through them real quick. Temperature, velocities, and concentrations all affect the rate of the reaction. For a reaction to happen, molecules must collide. They've got to collide with each other. But those collisions have to be effective collisions. As I mentioned before, if temperature increases, the velocity of the reactants increase. But data has shown that the reaction rate is still observed to be much smaller than what we would calculate should happen. That's because of those two criteria. The individual reactant molecules, number one, have to have sufficient energy to achieve the transition state, the activated complex, and they've got to have an orientation that provides an effective collision. If a molecule does not have those two things, it won't react. Okay? You need to study page 10 of this note very carefully. I don't want to read to you because that would insult your intelligence, but read it. If you have questions, email me or text me on Remind. Also, page 11 of your notes. That's more of the collision theory. Now, for the quantitative stuff, if you look on page 11, do you have any questions about collision model? Not yet? Anyway? Okay. All right. Quantitative. The book goes through and derives this equation. You will not have to derive it on my test or the AP exam. So we're just going to cut to the chase. There is an equation that accounts for everything I just described to you. The collision frequency, how frequently the molecules collide, that's going to affect rate. Because they got to collide for anything to possibly happen, right? Okay. If you look on page 11, you'll see that the letter Z stands for the collision frequency. And P is a variable that is called a steric factor. It is always a fraction, less than 1. And it describes the fraction of reactants having effective collisions, having effective orientations. You got to have an effective orientation to have an effective collision for reaction to occur. And then we have a term E to this exponent, negative of activation energy over ideal gas constant, Kelvin temperature. And this represents the fraction of reactant molecules with sufficient activation energy. All of this affects rate constant. All of those things affect the rate constant. All of that is described in a collision model qualitatively. Okay, so there is an equation named after a chemist named Savant. I'm probably mispronouncing his name. Arrhenius. We'll hear his name again when we get to acid-base equilibrium. He was the first to define an acid and a base. The Arrhenius equation is often written as, where's this fellow's name? All right, so the Arrhenius equation you see on page 11 of your notes. And where did that capital A come from? They just A equals collision frequency times steric factor. So the notes say that if we plot this equation, natural log of rate constant equals negative E sub A over R, and I think this is how it's written on your equation sheet. Not sure, I'll have to look. If we plot y equals mx plus b, if we plot 1 over temperature on the x and natural log of rate constant on the y, if we get a straight line, that represents what? Negative E sub A over R. And from that, we plug in ideal gas law, and we have activation energy, numerically. And I'll check when here in a minute and make sure that that is the form that's on your equation sheet. Well, I'm theirs. They took, okay, well, if I do know, I feel fairly certain, boy, they didn't put much at all on there, did they? Darn. Okay. I feel fairly certain right now that if you needed it, you would be given information, because they are trying to get away from you just memorizing stuff. Okay? But I'll check it out. I'll look at whatever samples are available of the exam and let you know if that's something that we need to be concerned with. But this equation will work with. What time is it? Y'all take a look. $5.86. Sample exercise 7. Okay, it says we have a reaction of 2 N2O5 forming 4 NO2 and plus O2. It was studied at several temperatures and rate constants were obtained. We got a table of rate constant and temperature, and they want us to calculate the value of activation energy, E subscript A. Okay, so look at how they do this. Everybody grab, you got your calculators handy? Let's plot it. It says that all you have to do is use this equation and make this plot. Make this plot. So let's just punch it in real quick. Okay, so we're going to go to list, stat list, stat edit. I'm in a hurry, can y'all tell? We got to clear our list. Crap. Hey, you know what? Since the girls are not here and they're going to be dependent on this video, let's do this when y'all come, either before or after you come back from voting for maids. And let's go ahead and talk about catalysts. It's real short and sweet. Okay? But I just want to say right now officially, if you were asked to take a table like this one that has rate constant values and temperatures, then you are simply going to create this plot, knowing that the slope is, this, right? Negative E sub A over R. You plug in R. Which value of R do they use? 8.3145? Yeah. And then you solve for E sub A. We'll practice it, but let's just move on. Okay. Catalyst. Catalyst. I can't spell. Okay. We have two types. We have heterogeneous. We have homogeneous. I can't spell today. This is on page 12 of your notes and page 588 of your textbook. Heterogeneous, this is where the catalyst is a different phase, state of matter from the reactant. And usually it's a solid. Usually it's a metal. Homogeneous, the catalyst is in the same state of matter, same phase as the reactants. Okay? Okay. What is a catalyst?
Something that speeds up a reaction.
Speeds up a reaction. Here is a more intense definition. It provides a different pathway for the reactants that has a lower activation energy. So going back to our graph, this graph would be without a catalyst. With a catalyst, we might have something like this. A lower activation energy would mean that more molecules would have sufficient energy. This would be with catalyst. Lower activation energy means more particles will have effective activation energy to get over the hump and make products. More will have form products. I'm getting tongue. Okay? Y'all good with it? Okay. Heterogeneous, usually you have something like this. You've got some sort of metal, and it provides a surface area. You have reactant molecules placed onto the surface of the catalyst. That is called adsorption. They move around on the catalyst surface, they collide, they form product. When product forms, it leaves. desorption. Okay. Zero order reactions usually require this. All right, how many, do you want me to go take a break? I've got like 2 more minutes. Okay, we'll take a break. Okay.
No, she got pulled
Okay. So, we are still recording. If you will take a look at page 12 of your notes. Remember, a catalyst speeds up the reaction. You need to, if I didn't get this in there, you need to add it. Yeah, you need to add this to your notes. How does a catalyst speed up the reaction rate? It provides a new pathway with lower activation energy. 12.
It's on here. It's on here.
It is?
Where?
Okay, where?
4 little paragraph thing, or 5 little paragraph thing.
Okay, yeah.
Where,
Right, where I've got written figure 12.6. So let's take a look at figure 12.6. Figure 12 point, that doesn't sound right. No, I've lost my mind. It is figure 12.17. I don't know. I'm sorry, your teacher is about ready for the leave-in.
Same thing.
I think she just went in the.
I guess it's a good thing y'all are graduating this year, because I might be in a straitjacket next fall. I don't know. It's figure 12.
Sorry for the interruption. Can I have everybody's attention? I need the senior class, 12th grade, to report to the junior high gym.
Every year it's like a bit.
On page 12 of your notes, 4 steps of a heterogeneous catalyst. The first thing is I have here, it's on page 590 of your book, which is a better drawing, actually. Page 590, figure 17, it shows the 4 steps that occur whenever a heterogeneous catalyst is used. Number 1, adsorption, which simply means the reactants come in contact with the solid catalyst. They land, you might say. They move around. The reactants achieve their activated complex. They migrate, they react, and then they leave the catalyst. That's called desorption, and that's it. Okay, so that is heterogeneous catalysts.
Can you explain, like, the catalyst is the metal
Yeah.
sheet?
Uh-huh.
I'm not understanding how that speeds up the reaction.
It gives it a surface area for which the reaction to occur.
With our alum, like she said when she did her
Lab.
the broken lab, we gave it something to grow off of.
Mm-hmm.
So that's what the metal does? It
Yeah.
gives something to grow off of?
Mm-hmm. Very good, Sarah. Thank you.
So how does it speed up
Because it gives a platform. It gives
for it to
a
start?
forum for it to happen. Just not in space. It's not all reactions. Just some reactions. This happened. This works with.
So heterogeneous is the metal. So
Yeah.
that would be like the zinc and the hydrogen that you use to make the hydrogen balloon. The zinc would be the catalyst.
No, the zinc was a reactant. Yeah, the zinc was going through single replacement reaction with HCl to make H2 and zinc fluoride. Okay. It's just that the zinc is solid, but it was a reactant. Maybe this will explain better when we look at homogeneous catalyst. On a homogeneous catalyst, the catalyst is in the same state of matter as the reactants. Okay? Here's the catch about a catalyst. The catalyst is present at the beginning of the reaction, and it's present at the end of the reaction. The catalyst is not a reactant. It does not chemically react with anything. Okay? Let me go back. Here's what a homogeneous catalyst might look like. We look at this mechanism. Let's see. N2 plus O2 yields 2NO. And this is a skill that you guys will do on the exam Tuesday. NO plus 1/2 O2. I'm just writing out the steps of the mechanism right now.
Ms. Branch, I hate to interrupt you, but can my 3 seniors come in here
Yes.
and see it?
Yes.
Thanks.
You're welcome. And did I write it down wrong? Can't tell. Okay, no, I'm good. Okay. Let's see. All of these are gases. I'm just in a hurry. That's why I'm not writing it. Light. And that's another thing. Light can be a catalyst. Let me back up on that one. Yeah, no, that's right.
Light is an energy.
Yeah,
How is it destroyed?
it lowers the activation energy required of the reactants. That's why you have to store hydrogen peroxide in a brown bottle, because the light will speed up the decomposition of H2O2, changing to H2O and O2.
What is O3?
Ozone. O3 is ozone.
How do you get just plain O?
It's a transition state.
Oh, because
It's a transition state. Yeah. So this is a reaction mechanism for the reaction of oxygen changing to ozone. There's the overall reaction at the bottom. So this is the mechanism. Okay, let's look more carefully at this. All of these are gases. All of these are gases. So we have a homogeneous catalyst. Let's find it. Okay. N2 is not the final equation, right? So it is either an intermediate or a catalyst, right? Intermediates. Intermediates are produced in one step and consumed in another step. Okay? Catalyst. Do I need to write it down? Are y'all good?
We're good.
Okay. Catalysts are present at the beginning of the reaction, and they are present at the end of the reaction. They are not, they do not react chemically. They're not, I mean, that might, I don't want to confuse you. Let me show you and see if it makes sense. For example, look right here. NO. Is it a catalyst? It's not in the overall equation. So is it a catalyst or is it an intermediate? It's an intermediate. Because it's produced here, right? And I think I've got it balanced wrong or something. I don't know.
On the paper, it's supposed to be 2.
Right
and
here?
they're using-
On the second one?
Yeah, it's really faded.
Okay.
Oh, is it on the notes?
Yeah, I was.
It's on the notes and it's on page.
And it's supposed to be a 2 and O2, but it's just really kind of faded.
It's also on page 594.
So Ms. Bunch, could you just look at that and say, since O2 is in the final product, it's in the beginning and it's in the end. Then O2 is your catalyst.
O2 is not the catalyst, it's a reactant.
Into your catalyst.
But N2 is not at the very end.
Hold on, let's, did I write it wrong?
What you wrote on the notes was 2NO plus half O2 produces 2NO.
Okay, yeah, all right, let's just do this instead of the notes. Let's do this instead. Okay, we don't have time, okay? Let's just try something else. I might have written that wrong. Okay, so let's do this to demonstrate it. Let's take a look at, number 61, page 603. Let me copy this real quick for the folks at home. Okay, this is number 61 in the problems. We have this mechanism, O3, plus NO goes to NO2 and O2. All right, that's a slow step. NO2 plus O goes to NO and O2. And the overall reaction is O3 plus O yields 2O2. This is what CFCs do in the ozone layer, by the way. Okay, it says on part A, which is a catalyst, which is an intermediate, and then they ask us to do a calculation. But let's take a look at A and B for the moment. Okay. O3 is in the overall reaction, so it's a reactant. So is O, and so is O2. So what do we have left? We have NO here, right? Okay. Okay, is it starting out or is it produced? No. Starting out. How do you know that?
It's right there.
Right, it's on the left of the arrow, right? Okay. And then it's on the right. It's not in the overall reaction. So NO is the catalyst.
Hooray.
Okay?
So if it starts in the reaction and ends in the product, it's a catalyst.
Yep.
If it starts in the product and ends in the reaction, it's an intermediate.
Yep. Bingo. NO2 is produced here. Very good, Sadie. NO2 is produced here. And then in another step, it's reacted, it's consumed. Yes. So NO2 is the intermediate.
They still cancel out also. They still cancel.
Yeah, they cancel. They have to cancel because they are not in the overall reaction. But do you see the difference? Catalyst starts out on the left, ends on the right. Intermediate is the opposite. Okay? And that's all you have to know about that. It's a homogeneous catalyst because it's all gases. I just didn't write it down. Okay? And that's it. Other than calculating activation energy, that's the end of kinetics. Okay, let's see if we can, real quick before you guys leave, do part C. And then we're done. Okay, on part C, activation energy, E subscript A, for the uncatalyzed reaction is 14 kilojoules. The activation energy for the same reaction when catalyzed is 11.9 kilojoules. What is the ratio of the rate constant for the catalyzed to the uncatalyzed reaction at 25 degrees C? That's kind of a weird question. Assume that the frequency factor A is the same for each reaction. I think they're just wanting a qualitative answer here. We're out of time, so let me check the cheat sheet. Oh, okay. Let's skip that because we're not going to ask that on the test. I won't ask that. What I will ask about activation energy quantitatively would be more like look at number 55. Look at number 55. That's what I would ask as far as math on the activation energy. Okay, on 55, it says we got a temperature of 25 degrees C. The first order rate constant, 2 times 10 to the third. 1 over second. Yeah. And activation energy is 15 kilojoules per mole. What does that mean? Those reactants need to absorb, for every mole of reactants, 15 kilojoules of energy needs to be absorbed to reach that transition state. And they want to know what the rate constant is. So what did I...
The rate constant is 75 degrees Celsius.
At 75 degrees Celsius, thank you. I should put that as a substitute. Okay. So you're going to use the Arrhenius equation. Yeah. So here's what the solution's going to look like. You're going to take Ln of the two rate constants, K2 over K1 equals E sub A over R, and then the difference of the two temperatures. Oops. Okay, so when we go through and solve that, we have, we're looking for the new rate constant, 2 times 1/3, our original rate constant, and our activation energy, 15 times 10 to the third joules. They change it to joules because of R. 8.3. And then you got to change the temperatures to Kelvin.
Which is on the phone?
Huh?
Where
Ideal gas constant. Okay, so then we punch all that in the calculator. and we get that ln of K2 over 2 times 10 to the third equals, do all this math, and it should come up to 0.87. Y'all try this, and then make sure you can get it. So then we are going to isolate K2. So we have K2. How do you undo a natural log? E, right? So if we take E here, right, and then we got to take E here, right? Okay, so we're going to end up with that undoes that. We're going to have K2 over 2 times 10 to the third equals E to the 0.87. And then finally, that will give you K2 equals 2.4 times 2 times 10 to the third, which is 4.8 times 10 to the third mole per second. So punch that in. If you're given the equation, you just do the math. But I want you to practice this weekend catalyst. I'd like for you to please do what they have in here. I don't like any of them. I don't like any of them. Study the one that we just did on identifying which is a catalyst and which is an intermediate. There's no practice sample problems, so I think we're done. So all I can say is get your homework in, study. We're going to do this Tuesday. I'll be here early for tutoring if y'all want to come in, if you can. I'll have a good long weekend.